All right. Hello, everybody, and welcome to session 2 of my character materials and rendering workshop. During this stream, I'm going to be talking about Albedo Maps, Diffuse Shading, and texture file formats. Um, and while that might seem like something that most people are fairly familiar with, I'm going to dive a bit more into how things like albedo can be captured, how you use albedo and or diffuse, how it affects the final shading of whatever you're looking at, and how it interacts with different layers of rendering, whether it's specular or normal, or basically anything else that you can use. Um, so just to give kind of a quick rundown, let's take a look at a model that has uh, some nice albedo, specular, and normals on it, and then we'll go from there. So this is a model that I made a while ago. It's some fan art of World of Warcraft. I really liked some of their designs, and I wanted to make something that was cool in their style, so I basically went ahead and did that. So you can see that this model has a few things going on with it. It has a lot of really shiny sections, such as here on these gems. You can see the reflections. You can see the reflections on the metal. You can see that on places like the hair, there's not too much not too much in the way of reflectivity and stuff going on, but there's still some shading information in the normal maps you can see, especially in deeper cuts in the normal, like right here. But what we're really concerned with during this stream today is what the hell albedo is and how it affects things, how it affects your shading, and how things like specular will affect your albedo. Additionally, I'm gonna just barely touch on metalness and what it does to albedo, and then from there I'm gonna transition into talking more about the file formats that you would probably be using in, say, a production environment, how different file formats are useful or not necessarily very useful, which file formats are useful for which types of textures. And I'm just going to very briefly touch on some compression and other stuff, just so that you can have kind of like a nice basis of knowledge, even if I don't get too really deep into that type of thing. Because honestly, I'm not. I may know some technical stuff, but I'm not familiar with enough of the different types of file compression and such to speak with too much authority on them. However, I know the basics, and I just want to communicate some of the basics to you guys so that once you get into a production environment, or once you're asked while you're at work to do something that has something to do with compression or different file formats, you have sort of a nice way to approach things. So let's get started on talking about what exactly albedo is, and we'll go from there. So, as many of you will probably know, albedo is more or less the same as a diffuse texture. Now, diffuse textures have been in computer graphics since we started using 3D, and or since the very early days of 3D, and it's basically just taking a 2D texture and slapping it onto some polygons. Basically, everybody knows that. Um, but how does that relate to the other textures that you might use, the other render passes or other things? Well, let's take a look at a flat shaded version of the same model. It has an identical diffuse albedo texture, but it doesn't have any of the specular information on it. So let's take a look at that right now. So this is that same model, the exact same model with the exact same diffuse texture on it. The only difference is that it has absolutely no specular information on it whatsoever. Additionally, there's no normal mapping, and it is being unaffected by any lighting. You can see that I have some lighting in my scene right here, and if I turn these lights on or off, it makes absolutely no difference. This is completely flat shaded. So all of the lighting information that you see, these reflections on here, the translucency on the gems, anything you see in these belts, all of that has been baked into this Albedo Map. And that's very useful for sort of lower end games, certain situations in film even, and it's great if you want to get details that look like World of Warcraft, Heroes of the Storm, certain aspects of things like Overwatch, Team Fortress 2. There are Dota. There are lots of games out there that still use lots of hand-painted textural detail like this. And then they just, add some stuff on top. So, great. Everybody's familiar with this stuff. If they're not, it's pretty easy to get up to speed on. But let's take a look at how Albedo is affected by things like Specular and Metalness. And we'll start to get an understanding of how those things relate to each other and how you can leverage one thing to change another. So let's go back to the one with the fancy shading on it. So here we've got that same model, and let's dive into its material right here. Now, I'm going to be jumping into Unreal 4 briefly later on, just to give a sort of real-world example of how you can build a very simple shader that takes advantage of diffuse textures and metalness and specular. It'll be extremely simple, but it will sort of serve as a way to get yourself acquainted if you've never built a shader before. And I'm going to do it in the context of what I'm talking about as far as Albedo is concerned. It'll be very quick though, so we're not going to be dwelling on it too long. But if there's some interest shown in it, I will dive back into Unreal 4 in later sessions to give more information on that. So let's take a look at this guy. So it's got the same diffuse texture on it, but you notice that all the gold trim and stuff is very, very shiny in comparison to what we had before. Let's just do a quick comparison here. There's the flat one, and there's the fancy one. Now, if I take this Metalness map and I turn it all the way down, what that's doing is it's going from having, it's going from having metal in these white parts. You can actually see some corresponding parts on here. You can see the spiky bits right here corresponds to these sections of the texture. It's taking the Metalness map is applying a higher specular value to those areas, to those white areas of the diffuse map, and at the same time, it is actually turning the diffuse in those areas completely black to make it so that the reflections show up much better, and it's much more in line with what you would expect from, well, metal. Metal is a very highly reflective substance, a very highly reflective surface, and so what that means is that when light reflects off it, it gets very little or no diffuse contribution to the final shader. So if we have a straight gray value for the Albedo map, and we turn it down, what the Metalness map is going to do, here, let me just close this up real quick. What the Metalness map is going to do is it's going to take those areas, these areas along here, anything that has white in it, any of these white areas, it's going to turn it to a very dark or even black color, and it's going to crank up the specular so that the specular matches whatever was in the diffuse. So this kind of gives you an idea of how metalness works in relation to a diffuse map. The metalness texture darkens the diffuse and replaces any specular shading that it had before with what was in the diffuse map. So actually, if I had a completely black area of my albedo, such as you might see here, and I turn down, let's see here. Oh, I know I can turn off, Oh, I guess I can't turn off Fresnel shading with Metalness. However, if you have Specular selected, let's just switch that over. You can turn off Fresnel, and if you turn up the intensity of the Specular, you'll notice that all these areas become bright white, even when the diffuse color is black. So that's reflecting a ton of information. So I'm getting a little off track here. I apologize. So when you have a completely black albedo map, instead of the specular map being a bright white color like you're seeing here when using metalness, using a specular map, it'll just crank everything up. So that's how things kind of relate to specular and to metalness when you're talking about albedo. Now, let's talk about diffuse shading. Diffuse shading is what happens when you don't have any specular information, but you do have diffuse information, or albedo, and you have a light in your scene. So let's just have one light in our scene. Let's turn off the sky, and let's just do some very simple diffuse shading. Actually, and we're going to turn off the normal map as well. So this is completely diffuse shading. Diffuse shading is, well, let's take a look at a simple ball. It'll be easier that way. And let's take the gloss, turn it all the way down, and the reflectivity, turn it all the way down. Turn the sky off, and let's just put one light in here. So here is a simple sphere with absolutely no specular or normal information on it whatsoever. This sphere is completely diffuse shaded, which means that a bunch of rays are coming from this light, sort of like you can see here, and they are being, the computer is determining which portions of the sphere are being lit by taking measurements from the surface of the sphere and tracing them back to the light and illuminating on a per pixel basis whatever you see on the screen based on how close they are to the vector of the light. So this light is shooting out vectors in these sort of rays, and then it's bouncing these rays back towards the camera. Let's turn off shadow casting, and you can see that there's that sharp terminator line. This is exactly the same thing that happens with the moon, and it's a fairly simple concept. Let's take a look at Unreal, and let's just make a quick diffuse shader. So here we have the shader for this little table right now, and it has several different inputs. The one that we're really interested in right now is the base color, because that's the one that's going to affect what we're doing the most. So let's just turn everything off at the moment. Let's do something that is just completely diffuse shaded. We're just going to do a simple flat color. It's going to be a white. Press OK. We'll hook that up to the base color. We'll just press save. Okay, it's processing that right now. And in a second, it's going to recompile this material, and this table will be completely white and completely diffuse shaded. Well, if it doesn't freeze on me, oh my, oh no. Well, it's, oh, there we go, and just popped back into existence. So here we have a table that is completely diffuse shaded. Now, if you want to have something a little more complex than that, obviously you can. There's lots of different inputs here. But let's talk about how diffuse shading and Oh, I'm sorry. It's been a long week already. Jeez. Let's talk about using albedo and ambient occlusion. So ambient occlusion, as most of you probably know, has to do with how light is blocked from around a model to give it nice deep cracks and crevices and stuff in your scene. So let's take a look at how albedo and ambient occlusion work together. First off, let's take this, turn off any emissive or anything else, turn all these things off. Okay, so that's looking pretty good. It's looking nice and flat. Now let's go into some rendering options and play with ambient occlusion for a second. Do, do, do. Oh my, oh my. Oh no, things are not going well tonight. Oh my goodness. And it doesn't want to work in there, so let's do it in Unreal. Well, this texture right here, if we take a look at the red channel, has ambient occlusion baked for this table. So let's take a look at this table. It has a round surface on the bottom, which corresponds to this spot on the texture, and then it has these legs, which are all mirrored. They're radially symmetrical, and they have ambient occlusion baked into all of it. So let's take a look at different ways that we can use ambient occlusion when we have a diffuse shaded model. Now, if you opened up this scene, it's the default scene for a blank template in Unreal. And you would notice that one of the things that they have hooked up in this shader is this little input right here. It is taking the red channel of this image right here, and it is multiplying it on top of some colors. The colors are masked out based on the green channel, so basically what this image is doing is it's taking some information from the green channel. It's saying for anything that's white, apply the color right here, and for anything that's black, apply the color right here. And that's a little mask. And then on top of that, kind of like a multiply layer in Photoshop, they just multiply the ambient occlusion. So let's plug that into the base color and see what it looks like. It's going to take its second for it to compile. And once it's done, you'll see that parts of this table are orange and parts of it are a light gray. They'll actually look very similar to these chairs over here. Here we go. So you can see that the top of the table is orange. Oops. Oh my. The legs are gray, and using the multiply layer, kind of like in Photoshop, or the multiply node, it multiplied the ambient occlusion onto the diffuse texture. Now you'll notice something. Parts of this table, let's just move that little sculpture out of the way. Parts of this table are not metallic, at least right now, like these chairs are. However, we can turn on the metallic. We're not going to do that right now because we're talking about just diffuse texturing, but we do want to understand how diffuse textures and ambient occlusion work together. So there are multiple ways that you can have ambient occlusion work together with diffuse. In this guy right here, I took a bunch of ambient occlusion and I multiplied it on some layers in Photoshop and did some painting and stuff, but you can see the results of it in places like this. This dark area was a direct result of ambient occlusion. However, this is not physically accurate because ambient occlusion is occluding ambient light, or it is the result of ambient light being blocked. Now, one would expect that no matter what the lighting conditions you're in, an object is going to stay the same color. It's just going to be affected by the light around it. So that's what ambient occlusion does. It simply affects the lighting of whatever is hitting your, or the lighting that is hitting your object, and takes some of that lighting out in areas that should be blocked, like the underside of this table. Now, you can put stuff like this into your diffuse, into your albedo. However, it's not going to be physically accurate. It's not going to be PBR friendly, is what a lot of people end up saying. And the main reason for that is that if you take a look at, say, these chairs, you'll notice that the light is coming from way over here. It's hitting the chairs on this side, and anything that is in shadow is just being lit by ambient light. So this is where ambient occlusion would come in. The ambient occlusion would occlude all the ambient light that is hitting the back here, and it would make little crevices and stuff be a little darker than anything else. But that shouldn't change the actual color of the object. All it's doing is changing how much light's hitting it. So what we're doing right here, where we're multiplying the ambient occlusion on top of our diffuse color, that's not right. That's not physically accurate. It's not something that's going to work in the real world. And if you turn this table over, you're going to notice that even if it's in direct light, let's just turn it so that the bottom of one of these table legs, yeah, there we go. So the bottom of this table leg right here is facing almost directly towards the light, and yet it's still this really dark gray color. That doesn't really make sense. You would expect that if it's made of a solid plastic or a metal or something, it's going to stay the same color. And this is why we don't multiply ambient occlusion inside our diffuse textures. Because under different lighting conditions, especially for characters, that simply won't work. So let's go back and change something about this table. Let's change how we use the ambient occlusion on this table so that it's a little more physically accurate, and if this table were a character, it would work in multiple different situations. Let's take the ambient occlusion from that red channel of this little mask image, and instead of multiplying it on top of the diffuse, let's plug it in to the ambient occlusion slot down here and see what the difference is. So we'll just plug those colors in to the base color and plug this red channel into the ambient occlusion slot, save that, and see how different it looks. All right, so there's not a huge difference in what we're seeing right now. You can still see that there's ambient occlusion happening under here, and the light is being blocked by the top of the table. The light's, the table's casting a shadow down here. But if we take this table and we rotate it so that some parts on the bottom are in direct light, you'll see that the only parts that are actually getting dark are the parts that are in shadow. Look at that. See how that little crevice back there is getting lit up, but then the parts next to it are getting that ambient occlusion? That is a correct application of ambient occlusion. Now, let's look at the unlit view. So it's completely flat shaded, or very close to flat shaded. And it's going to light correctly under any lighting circumstances all the time. Now, this is specific to modern rendering. This is not really going to work in something, if you're trying to get a job at Blizzard and work on, World of Warcraft or Heroes of the Storm, you're not going to really see this type of thing. However, if you're making something in Unreal 4, Unity, if you want to show something in, Marmoset or whatever, this is where you're going to be using ambient occlusion maps. You're going to plug them into the specific slot where ambient occlusion goes, and then it will only affect the ambient light. So let's take a look at ambient occlusion in Marmoset using an example we looked at last time. Let's open up this guy. Let's take just a second. All right, so let's take a look at this guy again. This guy has some ambient occlusion on him, but where? Let's take a look at where we can see some ambient occlusion on this guy and see where where ambient occlusion is applicable for characters. Let's turn off some of the more advanced rendering stuff just so that this performs a little better. Oh, we'll turn that back on. Okay, so we'll hide his hair, and we're going to turn off these lights. Now, this guy is just being lit with completely ambient light right now. And we can actually turn up the ambient light. Let's choose a different sky for this so that it becomes a little bit more obvious. This one's pretty dim. Let's do, Desert Road's pretty good. Okay. So this sky is being lit completely with ambient light from the sky. There's no directional light in here, at least nothing that you'd see like a spotlight, a directional light, an omni light, nothing like that. It's just being projected from this sky dome. And let's turn off this blue. Let's make it so that we can see the sky. Oops. Okay, here we go. So this is the ambient light that this guy's receiving. And we'll turn off some of the post processes too, just to make it a little more obvious what's happening. There we go. Okay, so as I rotate the camera around, you can see what color the ambient light should be on a given surface of this guy. So looking at this guy, you would expect that the light coming from directly behind him would be a kind of purplish color, and the light coming from directly in front of him will be an almost white, very light gray. So we can rotate that around. You can see that he's just being lit with ambient light, and on his skin he has an ambient occlusion map. So let's turn that down. Turn it back up, down, and up. So what this is doing is this is not multiplying on top of the diffuse color, it's actually blocking the ambient light. So now let's take and put a light in our scene. Put a skylight in here. We'll make it real bright, not too wide, but enough to cast some nice smooth shadows. And let's rotate it around him. So if you take a look at his ear right now, or the area in his eye right next to his nose, they're being pretty brightly lit, right? However, if you turn this light off, suddenly they get very dark. What this light is doing is it is blasting out all the ambient occlusion. But if you take a look over here in the shadow where there's no direct light, the ambient occlusion is suddenly visible and strong. Let's go to the post processes. You can see that this ambient occlusion map can be cranked up or pushed back down. And let's try turning off the ambient occlusion map and just seeing what the regular screen space occlusion is like. So screen space occlusion is a little different from occlusion that you would see in a texture map in that it's approximated from whatever's in the scene as opposed to being put into a texture. That's probably pretty obvious, but I just want to make sure that people are aware. So here's what it looks like without any ambient occlusion. Here's how it looks with ambient occlusion. That's really strong, but it's enough. So that's sort of kind of a primer, a very general, basic look at AO and diffuse maps, albedo maps. Let's talk about how albedo is affected by normal maps, and how sometimes normal maps can affect more than just surface shading or how specular reacts. So let's turn this guy's normal maps for his little vest off, shall we? So we're going to go into his clothing. We're going to turn off the detail normals, and we're going to turn off the normal in general. Now, let's also just take let's take this and turn it way down. Yeah, okay. So right now we have a constant specular value being applied to his entire body. I'll talk more about metalness and specular a little later on. Just know that right now his entire body is receiving one constant specular value since I turned off the metalness map and turned metalness all the way down. All right. So he's receiving one constant specular value. And let's turn the gloss to one simple value so we can see it better. Okay, there we go. Now he has no material definition. It's just a little bit of specular and a little bit of color. So let's turn the normal map back on. Hey, that's pretty fancy. All right, okay, that's cool. Let's turn the specular completely off. No specular whatsoever. Oh. Uh-oh. Let's turn this post-process off. That's a little janky. We'll go back into Flare and turn that down. Alright. There we go. Ooh, gnarly. None of that. There we go. So, he's got no specular value on him whatsoever. This is just diffuse and normal. So as you can see, the normal map is affecting the lighting on this guy. It's affecting the diffuse shading like we talked about before. So he is only being lit with diffuse light. There's no specular light. There's none of those little mirror reflections. There's nothing like that happening. You can see that these little studs on his wristband, his little his little polycount his little polycount belt. It's all just flat colors. So when you're working with normal maps and diffuse, and you don't really have much much by way of specular to work with. If you're working in an older engine and you're using just diffuse and normals with maybe a constant spec value or no spec value whatsoever, you can find that one of the things that is a really useful thing to do is to pump up some of your normal map details with some diffuse. So let's do that. Oh, hey, okay. Let's look at this guy again. Oh, look. So if we turn off the normal map, you can still see that there is some lighting information that's painted in to the diffuse. We can pump it up a lot with a normal map, but it's just accentuating what you have there in the normal map. Fine, peachy. Now let's get to the sort of meat and potatoes of what we're talking about here. Acquiring albedo information so that we can use them with normal maps, with specular and metalness. Let's talk about that for a second. So there are a few different ways that you can acquire diffuse or albedo information for your texture maps. One of the best ways, obviously, is to just take it from something like a physical measurement. So the best ways that you can take physical measurements are to go to places that do 3D scans of people. Oh, geez. Oh, I'm sorry. I have an emergency in the other room. I will be right back. Keep that in mind. I apologize. All right, sorry about that, guys. Had a minor fire in the kitchen. The oven was being a little bit funky, so I apologize. I was starting to notice a smell there, which is why I was starting to ramble and wonder what was going on. So, uh, let's get back to it. I believe we were talking about acquiring and using albedo information. So let's talk a little bit about that. I've had a I've had a nice deep breath. I'm able to get back to it now. So yeah, it's important to be able to get either accurate or at least believable albedo information when you're doing physically based rendering. That seems like it's probably a given, since a lot of a lot of physically based rendering is used in very realistic settings. Something like Call of Duty. You would probably want to have pretty good stuff in there, stuff that's fairly accurate. And this is why it's important to acquire your albedo information from reliable sources. There are lots of good sources out there. I'm going to be providing some links later on to good places where you can go to get accurate albedo information, specular information, stuff like that. One of these places you could go is scientific papers. The problem with doing that is that scientific papers are, well, they're scientific papers. So in general, they don't lend themselves to doing stuff like this guy. This guy is in no way scientific. So if you don't know how to read a scientific paper, there are people who are out there who can read scientific papers, interpret the information for you, and then take it and put it into usable form. So some of these people, like Sebastian Lagarde of Don't Nod Entertainment, he actually put together several resources for people, including sheets that have both specular and albedo colors and values for various different types of objects and surfaces. Now, this is an important thing to do. It's important to get these accurate values because, one, if you don't have accurate values, everything is going to look wrong when you try to go and render it. So if we take this guy as an example, this guy actually doesn't have very accurate values for a lot of stuff. For example, his eyes and his teeth are way too bright. The values that you usually see for things like the sclera of an eyeball or somebody's teeth are actually much darker than what you would see on this guy. So let's take a look at his textures, and I'll show you what I'm talking about. So if you take a look at the albedo texture for his head, you can see that his teeth right here are just a flat white color. Now, in general, most people's teeth are actually sort of an off-white or even a pretty deep yellow color that looks white in comparison to their teeth, or to their gums and their skin and their lips. If you're trying to go for realism, you probably want to use values like that. If you're trying to get nice values for something that's not a character, something that's, say, a brick wall, there are other, there are resources that you can use to get values for that. For example, the value sheets from Don't Nod Entertainment. However, you can also use things like the Qixels Suite. They have a library of materials. I'm sure that you guys have seen some of them out there in the wild. You can actually go and sample the colors that they sample from physical objects and use them on whatever it is that you are using. And you will find, when you're looking at albedo textures, that lots of them, aside from the black areas that you see on this texture, a lot of them look kind of washed out, similarly to how this guy's face looks washed out. This face doesn't have a ton of information in it. Now, granted, he's a very stylized character. However, you'll notice that there's no shading in here. The darkest tones are in where his beard or stubble would be, and in the purple around his eyes. And those are just for stylization. However, if you go and look at, say, 3D scans of people's heads taken in 3D scanning settings, you'll find that they're extremely washed out. They have very little color information aside from flat colors with a little tiny bit of variation in them. And even some of that variation comes from the fact that it's almost impossible to get those textures without having a tiny bit of ambient occlusion baked into them, simply because people's faces and other parts of their body have skin texture. And naturally, there's going to be a little bit of ambient occlusion in those little cracks and crevices. So I'm going to be providing some links, as I said before, to good resources for getting solid and either believable or actually accurate albedo values. But let's talk about a slightly different topic now, something that's a little bit more related to things you'll run into in everyday production and things that will affect how your textures look when they're actually applied to your models. So I'm going to do something a little bit weird here. I'm going to open up Photoshop, and I'm also going to get this guy's normal map, which you can see right here, and I'm going to save it as JPEG and reapply it. So let's edit that. So we've got it open in Photoshop, and if you zoom in to this, if you zoom into this texture, you can see that it has some nice crisp little details in here. There's one of his eyebrows. You can see that there's some stuff for his nose and his eyes, and you can see that there are pretty sharp creases and such in this normal map. I'm going to save these. I'm going to save this file as just a JPEG to give an example of some things that can happen when you are dealing with different types of texture formats. So in production, in game engines, in situations where you are having to produce stuff which is then going to be shipped in a commercial product, you're never actually going to be able to ship it as a Photoshop file. Unless something weird happens and you have a very interesting game engine. Let's just save this to my desktop for now. We'll just call it head normal 01. There we go. Okay. And let's zoom in and let's turn off any of the subsurface scattering stuff. We'll just do straight Lambertian lighting. So in production, you're going to usually be using texture formats that are highly compressed, usually in the form of DDS, which is a DirectX format texture, which will plug in directly to the engine. But we'll talk about that in a second. So we have this nice lossless Photoshop file which contains all the information. You're never going to get any sort of compression in here, and that's what's applied right now. But let's apply that JPEG. Well, you can't really tell the difference, can you? Well, not yet. However, I saved that JPEG at 100% quality, which means that any compression is going to be hardly noticeable to the naked eye. Now let's do something that's a little bit closer to what you would probably see in a game engine. We're going to save this again as a JPEG, and we're going to bump the quality down to let's call it 50. Oh, what's this? Oh, I'm starting to see some artifacts. Let's save this. Go back here. Oh, well. Now, it's still not super obvious, but I'm starting to see a little bit of faceting in this area that wasn't visible before. Oh, and if we take a look down here, you can see on his lips, there's more faceting. Now what's happening here is the Photoshop file doesn't have any compression in it, which means that no information is going to ever be thrown away unless I specifically throw it away. But when I save it as a JPEG, it's going to throw away information to get the file size smaller. It's going to average out little areas in 8x8 squares, and it's going to start making it so that those little squares are all one color, which introduces this interesting little faceting artifact. You know what? Let's take it a step farther. Let's open up that file again, the original JPEG file, in Photoshop, and just start saving it and seeing what happens. So, one moment while I get that open. All right. So let's zoom into the eye like we had before. Oh, there we go. So, it might not be super visible on the stream, but I'm going to make it pretty visible in a second. So here's the original file. Here's the compressed file. Now let's try saving it again at 50% quality again. Save that. Go back to here. Yeah, it's getting pretty faceted. Let's go a few steps farther. We're going to save this at, say, 10% quality. Oh my, now you can see on his upper eyelid, this crease in here. Even on some of the smooth areas of his cheeks, you can see that there are these weird little patches. And that's what happens with compression. Now, compression is almost always present in texture files that you're going to be using. And unless it's for a very specific reason, such as for a high-end car, which requires that all of the surfaces be very, very smooth, you're going to start running into stuff like this, even on very high-end engines and games, and you're going to find that in a lot of cases there's simply nothing you can do about it. Let's turn off some of this depth of field so everything's a little crisper. And let's turn off cast shadows so that we can really see. Oh, wow. So this is actually something that I run into on a daily basis. The fact that normal maps especially get highly compressed. Now, there are lots of... I'm going to talk a little bit more about compression and normal maps later on when I get to the normal map section. However, this is something that's good to note at any point, really, is that anything that is not a very high, expected to be very highly detailed and seen up close is going to be compressed like this, and it's going to be very aggressively compressed because texture files are in general very, very large. Similarly to movie files and music files, texture files are one of the things that takes up the most memory on a disk when you ship a game. Therefore, if compression can be applied to them, it will be. And this is especially true for normal maps. Now, something interesting to note about compressing normal maps is that normal maps are they are based on RGB channels. However, when you compress a normal map, there's often an option in your engine for compressing normal maps. So let's actually compress a normal map right now. Let's go into Unreal. Let's just open this up a little bit. We're just going to dump a normal map into Unreal and see what happens to it. So let's see here. We're going to take this original normal map. We're going to save it as a Targa file because Targas are pretty commonly used in game development. Let's save it as head normal 2, just so that we're keeping nice naming conventions and everybody knows which one is which, even though they're different files. Now let's just drag this into Unreal and see what happens. Okay, we're importing it. Texture, head normal 02 was imported as a normal map. Okay. So let's look at this. We're going to scroll. Oh. Now if we zoom in here, we're going to see something pretty interesting. This is a very large texture, so it's not going to be as visible as something that would be, say, a 512 or 256 texture, but if we zoom in just a little bit, we can see around the eye that we're losing a little bit of information. So let's take a look at the different channels of this texture and see what's happening. Let's look at the red channel first. So you can see around the eye in the red channel, let's just take a look in Photoshop just to make sure that we're on the same page. We'll take a look at the red channel. Now you can see in Photoshop here that there are some very smooth lines, some smooth gradients in here that look real nice and crisp. But if we go back to Unreal, you'll notice some interesting stuff going on. There's a little bit of jaggedy stuff going on. There's this little tooth right here that's not present in the Photoshop file, or at least not as strongly present. There's a single little pixel there. So Omar has asked why targas are commonly used. Very, very thankfully, Andy replied, it's an old and stable format that stores an alpha channel. Lots of programs support them too for reading and writing. So targas are very commonly used for those reasons. Additionally, they give very predictable file sizes for given resolutions and bit depths. And actually, that's going to bring me to one of my next points, which is going to be talking about bit depth. So let's go back to here and look at compression settings. So you can see, let's just maximize this. Now, often when you import a texture into a game engine, you're going to see an option for compression settings. Now, Unreal is pretty smart about how it imports things, so when it sees normal in the name of something, it's going to just say, oh, you're importing a normal map, we'll automatically turn it into a normal map. So you can see here in this drop-down that there are actually several different compression settings. There's the default, which again, like I said earlier, I don't know every single detail of every single compression format. However, I will mention a few of them. The one that they use for normal maps is DXT5, which uses certain compression settings to compress certain channels of the normal maps. So we're looking at the red channel right now. Let's look at the green channel. You can see that, once again, there's kind of some sawtooth stuff going on with some compression, which really is a result of pixels being averaged out in certain ways according to a certain algorithm. If we look at the blue channel, well, we can't see it really well right now because it's very low contrast. However, a lot of normal map compression settings will actually completely drop out the blue channel of the normal map, because in general, what you see in the blue channel is almost completely white. And often, because it's almost completely white, it's safe to completely remove that channel. I'm sure that there will be lots of people who could comment more on this, but that's one very common way of compressing normal maps, is to make it so that instead of having a red channel, a green channel, and a blue channel, one for, up and down, or left, right, up, down, and then a little bit of depth, it's just completely gone. You only have the red and green channel. So there are other compression settings that can be used too. The default one up here at the top at least in Unreal, is one that's used for diffuse/albedo textures or textures that it can't identify. There's one that is specifically used for masks, at least here in Unreal 4, and there will be similar compression settings in other programs that you see. Grayscale, which would remove color information, or it is made for specifically grayscale textures. So anything that literally is just black, gray, or white. Displacement maps that can be 8 or 16-bit. Vector displacement, HDR, which means it's good for image-based lighting because it has a wider color range. You sort of get the picture. There's lots of different compression algorithms. But let's talk about how we can use bit depth to get around some of the problems that we often see with normal maps. So one problem that we often see with normal maps is that on large smooth surfaces, like we see on this guy, if you have a compressed normal map or a normal map that only uses 8 bits per channel, you're sometimes going to get weird artifacts like this where some colors are averaged out or it looks noisy. Let's do something a little weird here. Let's do something a little weird. We're going to go back to Photoshop. We're going to go to this JPEG, and I have an idea. Let's change this to from 8-bit to 16-bit. So 8 bits per channel means that each of these channels is represented by 8 bits, or that's the equivalent of 256 levels of gray. So you can have up to 8 bits of information in one of these. 8 times the God, I can't numbers right now, but basically that. So 256 levels of gray times 256 levels of gray times 256 equals out to about 16.7 million colors. However, if you have 16 bits per channel, that's, oh God, how many is that? 16-bit color. Let's look that up on the internet, huh? Good God, it's so many. It's millions. It is. I'm sure that actually Andy's here. He can probably type it out in the chat. But it is so many colors that if I go and I change this to 16-bit and then I just blur the whole thing, oops. We're actually going to start getting averaged colors that will make smooth gradients between this weird flat area right here and the weird banded area right here. We're going to start getting areas in here that look smooth, like smooth transitions. And that's something that you wouldn't necessarily get with 8-bit color. Let's do that right now. Let's just smooth it to 2 pixels. We'll save that as a Photoshop file this time. We're going to call this head normal 03. And we will drag it onto there. If I can find the correct window. There we go. So let's drag that onto there. So those colors, all those colors still exist, but they've actually been blurred out around the edges, and they have smooth transitions because 16-bit color has enough colors that it can blur between those very, very close values. Actually, the transition is so smooth you might not even be able to see it on the stream now. Oh, there we go. It's 65,000 levels per channel, or oh, let's see. That's a lot of zeros in that number total, but it's billions of colors in 16-bit. Now, this is not the best example of 16-bit color. let's actually put together an example using a handy dandy little sphere. Let's do a sphere. Import a model from the Marmoset files themselves. Just do that real quick. So this is a model that has a completely flat color for the normal map. It's just a little tiny 16 by 16 flat normal image. Let's do something in Photoshop to illustrate the difference between 16 and 8-bit color. We will do a little 512 image. We're going to fill it with plain old flat normal map color. And we'll just save this as, well, normal example 01. Now, we shouldn't see any change on the model yet. Oops. Well, there we go. So we don't see any change, at least not currently. However, if we do something like, let's start spraying some color in here. Using 8-bit color and a bit of dithering on our nice soft brush, we can see that with only 256 levels of gray and a transition between this gray color and black, we get a lot of noise. So let's take this very basic normal map, save that, and see what it looks like in Toolbag. This is an 8-bit image. We'll save that and come back in here. All right. So it looks weird. However, it is very useful for us because using 8-bit color, we get grainy stuff like this. Let's go back into Photoshop, undo that, make this a lot larger. We'll change the size of this image to 2048. And we're going to do the same thing, but with a much larger brush. Oh, all right. So you can see that even with a very, very large smooth brush, actually let's change the spacing on this so that it's even softer. So that's a nice big soft brush. However, if you zoom in, you still see, even with that soft brush, you see banding and pixelation. Let's save this and go back to Marmoset. Okay. All right. Well, it's better, mostly because it's larger and the brush size was a lot larger. However, if we zoom in again, once again we can see that there's some noise in there. It's not as obvious, but let's turn down the brightness of the sky just a touch. Oh, now it's getting more obvious. Let's do a quick levels adjustment in here, or curves adjustment, and we'll be able to see it even more plainly. Oh, there it is. Now you can start to see the banding. Turn down the brightness even more. There it is. So you can see a ton of banding right there. It's this grainy, noisy weirdness going on. And as we move the light across the surface of this very smooth sphere, we can see that even though we tried to make something that was a nice smooth gradient in Photoshop with 8-bit color, it still came out as noisy. Now this is something you'll see a lot of if you're using compressed textures and or 8-bit textures on large smooth surfaces. This can be a huge problem if you're making sci-fi characters, if you're making weapons. Often you'll find with being somebody who's working on characters, you might have to make some weapons for those characters. If you work at a smaller studio or you're not doing outsourcing, you will find that you have to make weapons, visors, helmets, anything that a character might use. And suddenly you start running into this problem where you have the limitations of the number of colors in your normal map. And if you're using if you are using 8-bit normals, this becomes a huge problem, especially with large smooth surfaces like the visor of a helmet or the eyes on a character. So let's try doing the same thing, but let's do it with 16-bit color. So we'll just undo that. Make sure this is 16-bit. Now let's try using a large smooth brush. Now you can zoom in, and zoom in, and zoom in, and really the only difference you're going to see is between two different pixels right next to each other, if you can even pick it out. I can barely pick it out on my screen, and you might not even be able to pick it out given the compression that goes into the online stream. That, or it might actually be accentuated. I might want to look at this on the stream to actually see that difference in color. Now let's try it with a gradient. Let's just do a gradient from one corner to another corner. Okay, there we go. Now we can start to see more banding. There it is. But this is a 2048 image. If you're on an image that's 512 by 512, and you do the same type of gradient, there's going to be a little bit of banding on the stream because of compression. However, if you start to zoom in a lot farther, it becomes less and less obvious. Let's save that, see what happens in Marmoset, and then do something crazier. Okay, so we saved that. We put it in Marmoset. Let's turn off the grain in here just to make sure. Okay, well, it's pretty smooth. I mean, granted, it's not going to be perfect. Now let's try doing that same exact experiment again using 8-bit color, and we can see how much worse it actually is. We'll go back to image mode, 8 bits per channel. We're going to do a gradient. Oops. Just do a nice black to white gradient. Or actually, no, we do want a black to gray gradient because that's the whole example, isn't it? Okay, there we go. So, nice black to gray gradient, and suddenly, oh my god, it becomes so much more obvious. So this is 8-bit color. Let's save that. Go back to Marmoset. And, oh, geez. So that banding right there, that's not actually, that's not even compression, that's not the stream being janky. This weird ribbed look is simply because it's 8-bit color. So this is something that's useful to know, as I said before, if you're going to be working with large smooth surfaces like, sci-fi visors or something like that. Just as one more small example, even though you probably won't be using this in production unless it's a very special case, let's try it with 32-bit color. Let's just go back to a nice medium gray. Oop. And do another gradient. Now once again, because of the stream, there is going to be some banding visible just because of the compression that it uses to compress the video. However, as we zoom in, it's going to be way, way less obvious. We'll save that, go back to Marmoset. Oh, and there is no banding visible whatsoever. Or at least, not much banding. There will still be a little bit of banding because it's a 512 by 512 image, but really most of the banding is going to come from the fact that I've done level adjustments on this image. Yeah, actually all the banding that you see, aside from a couple of tiny little spots where it did a little bit of dithering, is all just from the fact that I did a levels adjustment in Marmoset. Fancy. So, what else is what else should we talk about? I mean, we're talking about, you know, compression. We're talking about file formats. You know what? On the topic of file formats, let's talk about MIP maps. So MIP maps, if you're not entirely sure what they are, they're basically a way of storing multiple different versions of the same image in a single file. So a MIP map it lowers the number of calculations and texture fetches that you have to do when you are trying to render something at a distance and or as it's coming closer to you. I can save this. Oh, let's make sure that I have a DDS saving. Oh, I might not have it. Here we go. NVIDIA MIPster. So this is going to let me save this file, or at least it should. Oh, it's been forever since I used this, but we'll see what happens. Oh, it's running through a little script. Here we go. Here we go. So I am making some MIP maps right now. And basically what this does is it takes the same image and it expands it so that it's twice as wide, or at least for this visual representation, it's twice as wide. And then in that second half of the image, it resizes, or it copies the image, resizes it to half the size, so half the width and half the height, pastes it, and then does the same thing, and the same thing, and the same thing, until you're left with something up here in the corner that's only one little pixel wide. So MIP maps will fade in as they are as you're getting closer to your character in the engine, and what that does is it lowers the number of calculations that you have to worry about. It lowers the memory requirements. It lowers the number of images that the computer has to look up inside the engine. And all of these will be stored in the same texture file as a DirectX texture or some other proprietary format that a specific engine uses. Usually this process is automated and it just happens in the engine, and it's part of the process of importing the texture into the engine. However, this is something that's important to note, because one thing that happens when you're worrying about MIP maps, when you're worrying about level of detail, is that if you have unwrapped your textures so that things are very close together, and this is actually a perfect example of what not to do. If you have items on your texture that are very, very close together, as you start going down the levels in MIP maps, you'll notice that there's less and less information between those two different islands. So as you can see, these teeth start to get
so that they're only a few pixels high, and when you're drawing these teeth from a distance, or if you're on a system, if you are rendering a character on a system that can't handle the highest level of detail, what it's going to do is it's going to take this lower MIP and it's going to draw it on the geometry. And if you have islands that are close together, they start to bleed into each other. So if a person is playing a game on their computer, and their computer isn't super fast, they might want to turn the settings down. So that will start to select lower and lower MIP levels until finally the models that are drawing on screen might have, you know, a 128 by 128 normal map, and suddenly all their teeth are just a single little blob on that texture. So this is something good to keep in mind if you want to unwrap a character and be very efficient about it. Sometimes, even though you'll be wasting space, it's actually more efficient and better for the final display of your character if you have islands that are separated by larger amounts. So when you're talking about texture sizes, usually the rule of thumb is that if you have a file that is or a texture that's 2048 by 2048, you would probably want at least 16 pixels between your UV islands, so that as it gets smaller, the texture bleed into these different islands is not apparent. So Potato Jim says, so it's not reducing the file size, but it is reducing draw calls since the engine is only referring to one file. I actually can't comment too much on that since, like I said, I know some of the technical stuff, but not all of it. I'm not a rendering engineer. Usually draw calls, however, have to do with how many textures are being fetched and how many different calculations are being done in a specific material or shader in the engine. So I can't comment too much on that specifically, and it can also change from engine to engine because each engine will render things in different orders. Sometimes different passes will be combined so that you have fewer draw calls and render passes. There's a lot of stuff to take into consideration. So along with talking about file formats, we can also talk about alpha channels. So alpha channels are super useful in that they allow you to do all kinds of interesting masking and other stuff in your textures. And I'm sure some of you have used alpha channels before for things like transparency or translucency. I use alpha channels on this guy, on his hair, to make the ends here look a little rough. So you can see, if I turn on the wireframe, I actually set it to something a little more visible, you can see that I have all this cut out along the edge, and it doesn't actually correspond to the edges of the polygons. It just corresponds to something I arbitrarily painted in Photoshop, essentially. I did that with an alpha channel from the Albedo map. And in Marmoset, you have the option to just click the little checkbox that says use the Albedo alpha for transparency. A lot of engines and a lot of shaders will automatically load this in. If you're in Unreal, let's go back to that little shader right there. If you are in Unreal, there are different options for this. You have to change the blend mode to something like masked, translucent, additive, modulate. We can change it to translucent for now, and you can see that there's an input for opacity in the shader. In other systems, in other renderers and game engines, you'll see very similar stuff. And what that'll do is it'll allow you to put a grayscale image or a grayscale texture or whatever into that slot. So let's just make a quick little image with an alpha channel. Let's do another 512. We'll just paint some nice, pretty colors real quick. Doop-a-doop-a-doo. Doop-a-doop-a-doo. Oh, it's so artistic. It's beautiful. It's gorgeous. It has so many colors. It has all the colors of the rainbow. But it's not quite enough. But let's see what it's going to do. We'll save this. And we'll put that on his hair. We're going to give him some nice bright hair and see what we can do with it. Oh, let me just navigate to the right one. Haha! Alright, so we're going to load that into the Albedo slot. So we'll just drag that on right here. Ooh, oh, he's gorgeous. He's fabulous. He looks amazing. But you'll notice that he doesn't have the nice rough edges. So to add those nice rough edges, we can use an alpha channel. An alpha channel is simply another channel for your color map, or any other map really, that is just another 256 level of gray, grayscale color channel. This one doesn't. It won't display when you're viewing, your final image. It will only be read as a sort of secondary effect. But let's do something here. Let's save this. We added a nice new alpha channel. We'll save that. Just hit Control S and go back here, and holy God, his hair is gone. So, in general, when you're working with alpha channels, anything is white is going to be either opaque or a positive value that will be plugged into whatever you're using it for. And black will be, say, transparent or a negative value. So let's save that and see what happens. Oh, hey, he's got some transparency now. But once again, we're running into a problem. The problem being that this is using something called alpha cutout. So alpha cutout basically takes the average value somewhere in the middle of this gradient, and it takes the middle value and says, okay, this is where I'm going to cut off. I'm going to say that anything above that value is white and anything below that value is black, and there will be nothing else. Now that value can be changed with a threshold. That is what it is. It's the threshold is what controls that, and you'll see the threshold in an alpha threshold in most engines and transparency solutions. Basically, this determines where that halfway point is, where it's cutting things off above or below it. Now, this is alpha cutout, and it says everything is either black or white and nothing in between. However, there are other different kinds of transparency. For example, there's dithered transparency, which makes it so that it's just drawing a bunch of tiny little dots corresponding to the values in your alpha channel. There is additive transparency, which I mentioned last time, and that will often take into account the alpha channel that you have, depending upon what engine you're using. But we'll talk about alpha cutout for now, since it's a pretty interesting. There are some pretty interesting things to mention about it. One, alpha cutout as I said before, has that threshold. However, some engines simply don't have the option for alpha cutout. All they have, or sorry, they don't have the option to load alpha channels that have multiple shades of gray. Generally, these are older engines, but they are still around. You'll see them quite a lot in say online games where you have stylized characters with cartoony hair. And basically what that means is instead of having 8 bits of color in the alpha channel, it only reads a single bit, meaning that each pixel is not capable of displaying 256 levels of gray. It's actually only capable of displaying black or white. So 8-bit alpha and 1-bit alpha are the two most common alpha settings that you'll come across. If you are working with an engine that only reads 1-bit alpha, your alpha channels will act, instead of having nice smooth gradients like this, where you can get here. Let me do some slightly crazier shapes in here just to give some examples. Instead of being able to get nice round shapes like this by doing a threshold between black and white, what you'll see is, let's just fill this all with white, switch to the pencil tool in here, and you will see that it is, in those types of engines, it's completely pixelated like this. There's either black or white and nothing in between. So let's switch back over here, and you can see that the edges, they're being smoothed out, but you still get the sawtooth pattern. So that's the main difference between 1-bit and 8-bit alpha, is that 1-bit alpha only allows you to do a single continuous or a single switch between either white or black. Now there's an added wrinkle for this. Even though some engines don't actually support 8-bit alpha, alpha that has nice smooth gradients, some of them will actually read the texture and then apply that that threshold for you automatically, just as a part of how they read the file that you plug into the engine. So what you will end up with is that you might have a file that has nice smooth gradients like this, and maybe even some little things like this. And in the end, you'll get fairly smooth shapes that don't always have that grody sawtooth pattern. It might be a little bit of a smoother transition, or it might be a transition that is nice and rounded off, depending upon how they blend their pixels in the engine. So last thing I want to talk about is differences between specific file formats that you're most commonly going to be seeing. I kind of gone over a little bit of that here and there as I've been talking, and I've kind of gone over some of the restrictions of the different file formats, but let's take a look at 4 specific file formats, the fourth of which I'm not going to dive into too much because it's actually a label for multiple different file formats. So let's look at JPEG first. JPEG is the file extension that you see the most often anytime that you're using a computer, more than likely. So Dylan is asking, so even though it'll read it as a 1-bit, having the gray values helps to smooth the transition. Yes, and depending upon how the engine interpolates the values between pixels, sometimes that transition can be sharper or a little more crisp, but in general, if you are trying to do nice smooth curves like you see here, or you see here, it's often advantageous to use an 8-bit alpha even if your your engine doesn't actually support 8-bit because it will give you smoother transitions. It will give you nicer shapes. This is not necessarily the best example because I'm kind of being cruel to this texture, but yes, it is often advantageous to use 8-bit alpha even if your engine only supports 1-bit. So let's talk a little bit about JPEGs. JPEGs are the most common file format on the internet, and despite their usefulness, they are not often seen in game development simply because they basically throw away information. So what I mean by that is that when you have a JPEG, like I was talking about before with the normal map example, if you have a JPEG and you save it at the highest quality possible, it's still going to take some values in your image, and it's going to try to average them out a little bit so that the file size is smaller. So basically what that means is if you have a texture like this, where a large portion of it is a set of very similar colors. For example, this area right here, it might be very difficult to see right now, but there are some slight undulations in the texture. But those values right here are very similar to ones that are right next to them. So there's kind of a slightly purplish spot in the middle right here. And JPEG compression looks at that area right there, looks at the area next to it, and if there is a gradient of color happening between two adjacent 8x8 pixel squares, it tries to average out that little gradient so that it is one color and can be represented by a single value. That's bad. That's bad because if you are trying to use normal maps, what it's going to do is it's going to throw away some really useful information. For example, if you have a normal map that is specifically made for, say, the Unreal Engine, and it uses a specific algorithm for determining the direction of normals and such, saving it as a JPEG will throw away some of that information, which will make it so that in the engine it doesn't just look like it's a little bit compressed and it has those little squares like we saw on this guy's head, but it will also make it so that it's pretty much unusable under most circumstances because it's never going to light correctly. Let's turn off the wireframes in here so we can see this guy again. So that little area I mentioned before is right back here. Now it's not perfect, but and part of that is because the normal map that I'm using is only 8-bit. But you can see that this light, the terminator of this transition is not 100% smooth. Part of that is because the normal map I'm using is 8-bit, and part of it's because this is the this was not baked in the most not in the best way, so it's not 100% accurate. If you use a JPEG for this texture, however, it's going to be even less accurate under every single circumstance. Now, if you're trying to do things like image-based lighting, JPEGs are also terrible because what will happen is as you are combining multiple different exposures to make a high dynamic range image, you're going to be cutting off some colors that you could potentially be using to light your scene or your character or anything that is using that image-based lighting. JPEGs automatically throw away color no matter how uncompressed they are, which means that they're not very good for doing what we do. However, because of their small file sizes, they are useful for using on things like the internet. So let's talk PNG for a second. PNG is also a fairly common file format. The difference between PNG and JPEG is that, well, actually there are a few different differences. Let's make a nice PNG out of this image. So a PNG, there are multiple different ways that you can make a PNG. One of them is to have a PNG 8, which, much like a GIF or GIF, or however the hell you want to pronounce it, is only capable of displaying 256 colors. This is the entire table of colors in this image that a PNG 8 is capable of displaying. Now, a PNG 24 is capable of displaying the same number of colors as a JPEG, which is about 16.7 million, because each of the color channels is 8-bit. However, a 24-bit PNG also has the added capability of adding transparency. 24-bit PNGs will actually display as transparent if they have an alpha channel. So you can save that out of Photoshop, and this little checkered area will be transparent. But there's something else that's interesting about PNGs. PNGs are also great because they are uncompressed. They don't apply any sort of lossy, well, they're not uncompressed. They don't use lossy compression, which JPEGs use. They don't average out the colors, and they don't try to compress things into little 8x8 squares and then average them out and do stuff like that. This leads to larger file sizes with PNGs, but it also means that they have much more accurate color. Finally, there's something else that's interesting about PNGs, and something that makes them pretty useful for game development, and that is that you can use 16-bit color with PNGs. So if I wanted to save a normal map and use 16-bit color with it and have it, have those nice smooth gradients, I could use a PNG, and as long as the game engine that I'm using supports PNG, I can save it as a 16-bit file and get all the color that I need. So PNGs are really flexible files. However, they do tend to have very bloated file sizes. Because they don't use lossy compression and they don't throw away any information, or at least the information they throw away is not important, depending upon the content of the image, they can be extremely large, especially in comparison to JPEG. Now, let's talk about TGAs. TGAs are probably the file format that you're going to run into the most when you're doing texturing for characters, or at least the one that I have run into the most. Depending upon the company that you go to, you might run into other file formats, but TGAs are very useful for a number of different reasons. The biggest and most compelling reason is that they always give very predictable file sizes. So let's undo that, and let's save this image. We'll save this as a TGA. We'll save it as texture example 2. And now it has some color information. It has some color settings here. We're not going to worry about that for now. We'll worry about that in a second. We'll just save it as a 24-bit. Press OK. Now, if we go to that file and we check its properties, we'll just open the little properties window right here. if we look at this, we can see that this 512 image is 768 kilobytes. Now, if we resize this to a 1024, and we save it again, we'll just save that. Oop. It would help if I was actually saving it as a PS or as a Targa, wouldn't it? Let's just save that again. Do that. Now, let's do the same thing. Look at the file properties. Okay, so it's jumped to 3 megabytes. Okay, well that's a pretty freaking big jump. However, let's do something a little weird. Let's just flatten this, copy, and paste it into there. Now, you would expect, having worked and used JPEGs a lot in your time, and used PNGs, I'm sure, and used GIFs or GIFs or GIFs or whatever you want to call them, that having put some different information into here, the file size is going to change. However, if you save it with all of the same settings, we save this, go to save, press OK. Now if I go to that file on my desktop real quick and go to the properties, oh, it's still 3 megabytes. Wait. Let's resize that down to 512 again. It was 768 kilobytes before. Let's save over that. Press OK. Go to the properties. Holy damn. It's 768 kilobytes. It is exactly the same file size, actually. Actually, down to the byte, it will always be the identical file size that it is right now if it is a 512 by 512 image and you save it using 24-bit color. So what that means is that if you're using a Targa file to for your textures, you're always going to know what the file size is, no matter what the content of the file is, as long as it uses the same color settings. Now, 24-bit color in a TGA means that it is able to display 16.7 million colors. We'll not worry about why it says 24-bit instead of 8-bit. Really, it's just adding up 8, 16, 24. It's a weird convention, but there you go. Now, if we want to save this same file, but we want to have an alpha channel, that's going to bloat the file size a little bit because it's adding more data. It's adding an entire other channel, and it's actually going to raise the file size quite a lot. However, let's do this again. Look at those properties. Wait, did I have the right one? Goodness. Oh, I was saving as 24-bit. Derf. So saving as 24-bit doesn't save an alpha channel. However, saving as 32-bit will save the alpha channel. So let's take a look at that file size. 1 megabyte, or 1,048,620 bytes. And it's going to be the same no matter what the content of the RG and B channels, no matter what the content of the alpha channel, as long as it is a 512 image with an alpha channel, it is always going to be a megabyte. If it has no alpha channel, it's always going to be 768 kilobytes. If it's a 2048, it's always going to be the same size. If it's a 4096 or an 8192 or whatever, it's always going to have a very consistent file size. And what that means is that when you're using this in development, if you're using this as you're actually making a game, the people who are in charge of actually optimizing the contents of the disk that the game will be actually like physically printed on, or who are in charge of optimizing the size of the download, they're always going to know that if a TGA is being saved, it's always going to be the same size, so they can actually look for blocks of data that are those same size, compress them on the disk using certain algorithms, and it will actually make the file size smaller, and they'll know that they can look for those. And this is why TGAs are so popular. So Dylan asks, wait, so you could save a 16-bit TGA normal map and it wouldn't retain the info of the blue channel? So that's a very, very good question. TGA, that is one of the limitations of TGA. It's one of the biggest reasons that TGA is not used for certain things. And that is that TGA only supports 8-bit color. Now granted, TGAs are super useful if you have like a color map or a gloss map or something like that. But no, it does not support 16-bit color, so they're not always the best format for normal maps. However, for basically every other type of texture, TGAs are super, super useful because you'll always know what the file size is. And this is why you'll see them so often in production environments, and it's one of the good reasons that you should familiarize yourself with them so that you know when you're using too much memory. If you're using a texture that's too big or a texture that's too small, if you could be getting away with using more texture data, maybe you want to be doing that. So, Dylan also asks, file saving. The way he was saying the 24-bit is actually 8-bit, it's just reading the 8-bit per channel. Yes, so when talking about color in, say, a Photoshop file or something, 8-bit refers to how many bits per pixel per channel of color information you have, or how many values in one of these grayscale channels you can have. So 8 bits corresponds to 256 values, from 0 to the number 255. And you can actually see that on these little sliders up here. They only go up to 255 instead of 256 because everything starts at 0 and goes up to 255. And that's how many values each one of the color channels can have in it. Now, for 16-bit color, it's much higher than that. It's thousands of colors per channel. And that's what you might often be using for normal maps, but TGAs only support 8 bits per channel. The reason that they say when you go to save as a TGA, do you want to save it as 16-bit, 24-bit, or 32-bit, is that 16-bit means that, 24-bit is just adding up the number of bits per pixel, and just saying, this is how many bits per pixel you can have if all those bits are added up. The same thing for 16 and 32. 32 refers to the fact that you're just adding another 8 bits on with the alpha channel. It's not actually adding color information to any of these channels. It's just saying, oh, you're adding another color channel. 16 bits per pixel, if I'm not mistaken, is the same as saving it as an 8-bit PNG or a graphics interchange format file, since I don't want to bother with the pronunciation for that. So I'm going to be stopping the stream in just a few minutes here. I hope this has been somewhat useful for you. Again, I apologize for rushing through some stuff at the start and the little emergency that I had in the other room earlier. I'll try to avoid having oven fires in the future, but you never know. I will be doing more streams next week on Tuesday and Thursday at the same time, 7 p.m. Pacific Standard Time. And they will be going for 2 hours, and then I'll be switching over to a Google Hangout with the people who signed up for the actual for the program on Patreon. Anyway, if you guys have any questions, feel free to post them in the chat. I'm going to be shutting down the stream in about 5 minutes and then going over to the private channel. But I'll be happy to answer if I can. And if I can't, I'll at least try to give you information on where you can go to look for whatever you need to know. So yeah, once again, thank you for joining me. And if you'd like to, learn about specular and gloss maps and metalness and roughness and things like energy conservation and stuff like that, I'm going to be on next week on Tuesday at the same time, same bat channel. So feel free to stop by. And yeah, once again, the first 2 hours will be completely free for anybody to watch, and I will be posting the recording of this stream on YouTube tomorrow. I'll be posting the streams from next week on YouTube the day after, so keep an eye out if you can't watch the whole thing, etc., etc. So Midori Koishi asks, just a quick question: are GIFs or GIFs or whatever you want to call them really used anywhere in production? In my experience, no. They do not have. They're only capable of displaying 256 colors, which is not super useful in most cases. The only times that I've seen them are in animations that people put into the the internal chat system that we have at work, and usually they depict coworkers in compromising situations and or making very funny faces. That's the only place that I've seen them in production. I would love to hear from somebody who has used them in production. I think that would be great to hear about. I suspect that they were probably used in production several years ago, but have not been in use for quite some time. Does anybody else have any other questions? Overson SG asks, next time you're going to be doing the difference between PBR metallic and PBR specular. Yes, I'm going to be talking about the differences between specular and metalness. I'm going to be talking about the workflow, and I'm going to be talking about what specular actually is, how it's used, how you can author specular maps, and the different types of specular that you might run into. Regular, normal, everyday specular, anisotropic specular. I'm going to talk about metalness and how it relates to specular. And I'm going to talk about gloss and roughness, how they relate to each other, how they relate to specular and or metalness. And I'm also going to talk about things like energy conservation and Fresnel and stuff like that. So yeah, keep an eye out. It should be a pretty good one, and I'm pretty excited to get on that stream because it's something that I really like talking about. Did anybody else have anything they want to ask before I sign off in a couple of minutes here? Oversen SG also asks if specular and or metalness is more physically right, or I'm assuming you mean physically accurate. It's an interesting question. I will be talking about that next time. I suppose let it suffice to say for now that both Metalness and Specular have their place in physically based rendering. One of them, I would say, is a lot closer to how you might expect real-world materials to behave. However, they both have their uses, and they're both very good ways of working in certain situations. And I think with that, I'm going to shut down the stream. So once again, thank you all for coming. I'll be back at the same time next Tuesday for talk about specular and gloss, metalness, roughness, energy conservation, and all kinds of other fun stuff. So I hope to see you all there, and you guys have a good night. And now I'm going to jump on to the private stream with the subscribers. I'll see you guys later. Have a good night.